Assalamualaikum and very good morning. We are from Group 3. We present to you about zeolite. My name is Anis Zulaika. My members are Nur Alia, Anis Auni, Nur Sabrina, Fatim Fakiha and Nur Fatma. So we go to the first slide. What is zeolite? Zeolite are aluminosilicate solid bearing a negatively charged honeycomb framework of micropores into which molecule may be adsorbed for environmental decontamination and to catalyze chemical reaction. So for the structure of zeolite, these are the characteristics of zeolite structure. Three-dimensional tetrahedral framework in which each oxygen atom is shared by two tetrahedra. Large cavities with the presence of water, and usually the diameters of the cavity is in between 2 to 8 angstrom for the easy movement of ion between the cavities. And the structural unit that compose the framework such as ring or polyhedral type. So basically, crystal structure of zeolite can be categorized by two, which are primary building unit, PBU, and secondary building unit, SBU. PBU, examples of the PBU is SiO4 and AlO4 tetrahedra. These combine by sharing oxygen atom with adjacent tetrahedra to form a spatial arrangement of simple geometric form, which we call it SBU. SBU come in a variety of form, which are single ring, double ring, polyhedra, or even more complex unit. These will link together in a variety of ways to produce a unique system of channel and cages. So basically, these are that we talk about. The primary building unit will link together to form secondary building unit, which will result in a cage. This example of a chemical model of complex zeolite structure. The differently sized hole represent channel and cages. So we can see that we have two sizes here, the small and the big. So in addition to PBU and the SBU unit, zeolite may contain other components such as double ring, cancranite cage, and alpha cavities. This will be appeared in several different framework structure and can be useful in identifying relationship between framework type. So the most common example of the CBU is a ring. The size of the ring are decided by the number of the tetrahedron in a ring. The size of the ring also will determine the pore size in the different zeolite, and ring may be joined to form more complex of CBU structures such as a prism and cage. So basically, the CBU is the small SBU secondary building unit is that are interconnected to form a wide range of polyhedra. So to summarize the structure of the zeolite, we can see this picture. We have a primary unit, and then the primary unit are connected through corners of sharing oxygen to form this secondary building unit. And then the secondary building unit are interconnected to form a wide range of the polyhedra, which we call it the composite building unit, which in turn the CBU will connect to form the infinitely extended framework of various zeolite structure. So I will pass this presentation to Fatma Ujang.
Hi, my name is Fatma and my method number is 192311. So I will continue the presentation with the chemistry that is related to the zeolite. Zeolite consists of two types, which is natural zeolite and synthetic zeolite. Natural zeolite mostly formed as a result from volcanic activity, and it is formed from the ejected hot lava and ash that move towards the sea, and it meets with the salt water. Over the million years, it's getting harder and forms the zeolite. The natural zeolite is contain impurities such as quartz that mostly found in the clinoptilolite. The benefit of natural zeolite is it provides the low cost treatment, it exhibits excellent selectivity at low temperature, and it also releases non-toxic exchangeable cation. The other type of zeolite is synthetic zeolite. Synthetic zeolite is formed synthetically manufactured. The synthetic zeolite have been synthesized by a process of slow crystallization of silica aluminum solution in the presence of alkali and organic template. The synthetic zeolite is more pure than the natural zeolite and it can be altered to fulfill the industrial demand. Next, I will talk about the size of pores and shape of the zeolite. The size of pores or cavity and the shape of the zeolite varies due to the presence of alumina. Aluminium cation replaces silica cation and it resulting the zeolite framework to exhibit negatively charged. It's required the additional counter ion or additional cation to maintain the neutral charge of framework. These cations are exchangeable and are fixed in the cavity of zeolite. Due to the different size of the cation, it affects the size of the cavity or pores of the zeolite. Also for the shape of the zeolite, the change in the aluminum content in the framework lead to distortion of the geometrical features. Thus, it affects the surrounding atom like the structural framework atom and the extra framework cation. Also, the change in the aluminum content in the zeolite affect the polarity of the zeolite. The polarity of the zeolite or synthetic zeolite can be controlled as it depends on the zeolite aluminum content. The adsorption capacity and selectivity of zeolite for polar molecule increase when the silica to aluminum ratio decreases. This is due to the increase of electric field in zeolite pores or zeolite cavities induced by the increasing number of charged sites present at surface of zeolite. This high silica zeolite or high silica to aluminum ratio have more homogeneous surface characteristic and it has exhibit high hydrophobic selectivity. So that's all for me. I will pass to Sabrina to continue the presentation. Thank you.
Thank you to Fatma Ujang. So I will proceed the presentation with the properties of zeolite. There are many properties of zeolite, but I want to emphasize on absorption and also ion exchange. So for the absorption, there are two types of absorption, which are physical and also chemical. So absorption, depending on the force and also interaction of adsorbate and also adsorbent. So this is the picture, show the physical and also chemical. The difference is the interaction occur. Physical contain van der Waals and also chemical contain the formation of new ionic or covalent bond. This process is much slower than this process because this process is not reversible and also have strong interaction between the binding site and also the molecule. For the ion exchange, the zeolitic framework are negatively charged and this negative charge is balanced by the presence of Na and also H+. Okay, so for this absorption or molecular sieve is to separate the straight change from the branch change in the gas chromatography. And molecular sieve is depend on size and also shape. If the size of the molecule is bigger than the pore of the sieve, so it cannot be entered. But if the size is smaller than if the size of the molecule is smaller than the molecular sieve, it can be entered. And adsorption process can be used also to remove polar H2O, H2S, and also CO2 from the natural gas. Okay, so this is about the type of the molecular sieve, which are type A and also type X. There are three types on type A, which are 3A, 4A, and also 5A. The difference between them is the element used, which are potassium, sodium, and also calcium. And the For the type 13X sieve, the pore size of about 10 angstrom and enables many branch chain and also cyclic compound to be absorbed. Okay, for the ion exchange, this process will be occur when there are presence of extra ion that located in the cage. So as you can see, the shaded one is the extra ion in the cage. The zeolite structure itself have various cation sites, and when the zeolite contact with electrolytic solution, the this cation will be escaped from the site and replaced by other cation from the solution, which are the electrolytic solution. And the zeolite modification play the ion exchange capacity mainly depend on the content of aluminium at their crystal lattice. Okay, for this is about enzyme and also scolecite. Okay, for the exchange capacity of enzyme is higher for sodium. So this is the series. The highest is Na and then the lowest is Li. For this selectivity sequence, the ammonium ion is the highest and the lowest are K and also Sr2 plus. For the scolecite, selectivity sequence depend on the temperature and also flow rate. But if at low temperature and also under static condition, the selectivity sequence is the most one is Sr2 and the lowest one is the N2 plus. Oh sorry, Ni2 plus. So I will pass the presentation to Alia. Thank you.
Hi everyone, so I will continue the presentation with the synthesis of zeolites. Many synthetic zeolites has been synthesized by a process of slow crystallization of a silica alumina gel in the presence of alkalis and organic templates. One of the most important processes used to carry out zeolite synthesis is soil gel processing. Soil gel processing is a method for producing solid materials from small molecules. The method is used for the fabrication of metal oxides, especially the oxides of silicon and also titanium. The product properties depend on reaction mixture composition, pH of the system, operating temperature, pre-reaction reaction time as well as the templates used. The synthesis of zeolites are carried out in liquid phase and there are three methods used which are the hydrothermal method, solvonated method and also ionothermal method. The hydrothermal method is the earliest method of synthesis of zeolite in which synthesis is carried out in the presence of water as solvent, base solution as mineralizer at the temperature range of 100 to 200 degrees Celsius. Since the temperature used is much lower, this method is much easier and cheaper than other methods. Nucleation and crystallization of the crystal do not necessarily occur in solution but can take place at the cells present in the mixture. For the solvothermal method, it involves the use of solvent to produce the zeolite. The hydrothermal method can also be said to be a member under this classification since water is by far the most common solvent. There are, however, other solvents such as alcohol, hydrocarbons, pyridine, and many more that has been successfully used for zeolite synthesis. The solvent used in the solvothermal method of zeolite synthesis varies from nonpolar and hydrophobic to polar and hydrophilic. For ionothermal method, this is another special category of solvothermal synthesis method in which the solvents used are mainly ionic compounds and are not molecular in nature as in the case of the solvothermal solvents. The solvents used in the ionothermal method of zeolite synthesis are called the ionic liquids, and their ionic nature has an effect of some particular properties. For example, it lowers the vapor pressure. This is an example of the hydrothermal synthesis process. This is the mixing and aging process. The amorphous reactant is containing a silica source, aluminium source, An inorganic cation, an organic structure directing agent (OSDA), and water are mixed to form an aqueous precursor. This precursor undergoes an aging process conducted either at room temperature or an elevated temperature to ensure adequate mixing and tuning of the precursor. And then this aged precursor is fed into a sealed autoclave and heated to the reaction temperature, which is 100 to 200 degrees Celsius. After a certain synthesis period, the autoclave is cooled down and the crystalline product is recovered by separation, washing, and drying. Thank you.
Okay, so I'll continue the presentation with application of zeolite in separation and purification of gases and liquid. So there are two applications that will be discussed today in this presentation. The first one is oxygen separation from air. So the oxygen can be enriched from air to purity of 90 to 95% by pressure swing adsorption. So this process uses nitrogen selective zeolites of type 5A or 5 Armstrong or X. So 5 Armstrong is the size of the pore of the zeolite. Due to the ability to adsorb polar compounds, zeolite is considered as excellent candidate material for separation and purification of gases. Zeolites have molecular safe characteristic to exclude some gas molecules from their structure based on the size of the molecules, thereby restricting the ability of larger molecules to be adsorbed. So basically, the size of the pore of the zeolite can be adjusted based on the molecules that we want to separate. So the smaller molecule can pass through the pores easily, leaving behind the larger molecule. So this larger molecule will be adsorbed into the framework, and much larger molecule cannot pass through the pore. Okay, next, zeolite have the unique ability to adsorb nitrogen more strongly than oxygen due to the interaction between quadrupole moment of nitrogen and the cation that is attached to the zeolite framework. Okay, so basically in this application, we want to separate nitrogen and oxygen from air to produce a high purity of oxygen. So the nitrogen is the size of the nitrogen is much bigger than oxygen, so the oxygen can pass through the pore easily, leaving behind the nitrogen. So this nitrogen will then be adsorbed into the zeolite framework. Okay, so next we will discuss on the process of pressure swing adsorption. Okay, so compressed air is fed into the first zeolite's bed. Nitrogen molecules are trapped while oxygen is allowed to flow through. So this is, as you can see, is the first bed. So when the adsorbent is in the first bed becomes saturated with nitrogen, the airflow feed is directed to the second bed. Okay, so that is the first bed. So the first bed is become saturated. So this is the second bed. Okay, the adsorbents absorb nitrogen in the second bed. The first bed is depressurized, allowing nitrogen to be purged out of the system and released to the atmosphere. So basically, depressurized means they will lower down the pressure so that the nitrogen will be released to the atmosphere. Next, the process starts over. Compressed air is once again fed into the first bed. The second bed is depressurized, releasing argon and nitrogen molecules to the atmosphere. The process is repeated continuously, producing a constant flow of purified oxygen.
So the second application for liquid is water purification. Water purification is process of removing any contaminant from the water, for example salt or spill oil, by a membrane with a hard salt oil rejection and water premations. The zeolite in the membrane have excellent molecular serving and mechanical properties as a potential alternative in the reverse osmosis membrane. So for example, a natural zeolite HEU type membranes were fabricated to remove a metal cation and toluene from synthetic seawater at the 85 degrees Celsius and 180 m under a prefabricative evaporation. So these are membrane show rejection rate of metal cation and toluene. Another example of zeolite application is coated mesh film for gravity-driven oil water separations. Water can be separated from oil. Water is driven down, follow the gravity, and oil is left on the film. Film is were fabricated with growing crystals of silicate on the stainless stain meshes. So the further explanation you can see on the link below.
Hi everyone, we are from Group 3 presented to you a video entitled Zeolite. Zeolite consists of two types, natural zeolite and synthetic zeolite.
Natural zeolite is volcanic materials created over millions of years through the interactions of volcanic lava and ocean water. It embodies all four forces of nature: air, earth, fire, and water. The uniqueness of zeolite is having unusual micropore structure that give the material its characteristic shape with tremendous number of cavities which are connected into channels similar to a honeycomb. These hollow spaces account 24 to 32% of the total volumes of the materials. Zeolite functions as a kind of mineral sponge, and zeolite structure captures solid, liquid and gas from the materials. Zeolite has unique negative charge, making it perfect for absorbing various contaminants such as heavy metals, toxins, ammonia and radioactive material from the environment, the atmosphere and even living organisms. Synthetic zeolites are produced in the forms of mononuclear asteroids which have different microcrystalline structure. The input window of the molecular lattice can vary in size from 2 to 15 angstrom, depending on what chemical process the zeolites are intended for. But their main purpose is dehydration, purification, and separation gases and liquids. Separating different molecules is achieved by altering the size of the input window. Depending on the size of the window, only certain size molecules are absorbed onto the zeolite surface. For example, water molecules are smaller than both carbon dioxide and oxygen molecules, and those so easily trapped by zeolite crystalline lattice 3 angstrom wide, whereas other molecules simply bounce off the surface.